Welcome everyone. Today, we'll discuss the failure of metallic structures due to microbiologically induced corrosion, or MIC, and explore techniques for protection. This topic is critical for industries relying on metal infrastructure, as MIC can lead to severe economic and safety consequences. Overview of microbiologically induced corrosion or MIC and its significance. Microbiologically induced corrosion or MIC is a complex phenomenon where microbial activity accelerates the degradation of metallic structures. MIC occurs in various industrial environments such as pipelines, storage tanks, and marine structures, leading to severe economic and safety consequences. The presence of microorganisms like sulfate-reducing bacteria or SRB, iron-oxidizing bacteria, and other biofilm-forming species creates localized electrochemical conditions that promote corrosion. MIC is significant because it accounts for a substantial portion of corrosion-related failures globally, often resulting in costly repairs, environmental hazards, and operational downtime. Understanding MIC is essential for industries such as oil and gas, water treatment, and marine engineering, where metallic infrastructure is critical. This introduction sets the stage for exploring the mechanisms, types, detection methods, and protection strategies against MIC. Biological and chemical processes driving microbiologically induced corrosion or MIC. The mechanism of MIC involves a synergistic interaction between microorganisms and electrochemical reactions on metal surfaces. Microbes form biofilms that create microenvironments with distinct chemical properties, such as low oxygen concentration and high acidity. Sulfate-reducing bacteria or SRB play a major role by reducing sulfate to sulfide, which reacts with metal ions to form iron sulfide deposits, accelerating corrosion. Similarly, iron-oxidizing bacteria promote rust formation by oxidizing ferrous ions. These processes disrupt the protective oxide layer on metals, exposing fresh surfaces to further attack. MIC often initiates in crevices, under deposits, or in stagnant zones where biofilms thrive. The localized nature of MIC makes it particularly dangerous, as it can cause rapid pitting and structural failure without obvious external signs. Understanding these mechanisms is crucial for developing effective prevention and mitigation strategies. Forms of microbiologically induced corrosion or MIC-related corrosion. MIC can manifest in several corrosion forms, each with unique characteristics and implications. Pitting corrosion is the most common, where localized holes penetrate deep into the metal, compromising structural integrity. Crevice corrosion occurs in shielded areas such as joints and gaskets, where stagnant conditions favor microbial growth. Galvanic corrosion can be induced when microbial activity alters the electrochemical potential between dissimilar metals. Uniform corrosion, though less frequent in MIC, may occur when biofilms cover large surface areas. These corrosion types often coexist, making diagnosis and treatment challenging. Visual inspection may reveal tubercles or deposits, but the underlying damage is often more severe. Understanding these corrosion forms helps engineers design targeted protection strategies and select appropriate materials for MIC-prone environments. Detection techniques for microbiologically induced corrosion or MIC. Detecting MIC requires a combination of visual, chemical, and microbiological methods. Visual inspection can identify surface deposits, tubercles, and discoloration indicative of microbial activity. Electrochemical techniques such as linear polarization resistance and electrochemical impedance spectroscopy help assess corrosion rates and detect localized attack. Microbiological analysis, including culture-based methods and DNA sequencing, identifies specific microbial species responsible for corrosion. Advanced techniques like scanning electron microscopy or SEM provide detailed images of biofilm structures, while molecular tools detect microbial genes linked to corrosion processes. Early detection is critical to prevent catastrophic failures, and integrating multiple methods ensures accurate diagnosis. Industries often implement routine monitoring programs combining these techniques to maintain infrastructure integrity. Strategies for preventing microbiologically induced corrosion or MIC. Protecting metallic structures from MIC involves physical, chemical, and design-based strategies. Coatings and linings create barriers that prevent microbial attachment and moisture ingress. Biocides are commonly used to control microbial populations, though their effectiveness depends on proper dosing and environmental conditions. Cathodic protection, either sacrificial anode or impressed current systems, mitigates electrochemical reactions that drive corrosion. Material selection is another critical factor. Alloys resistant to MIC, such as stainless steels with high molybdenum content, offer better performance. Design considerations, including minimizing crevices and ensuring proper drainage, reduce areas where biofilms can develop. Combining these strategies in a comprehensive corrosion management plan ensures long-term protection and reduces maintenance costs. Let's summarize the key points. Microbiologically induced corrosion or MIC is a major contributor to metallic structure failures in various industries. Its mechanisms involve complex interactions between microorganisms and electrochemical processes, leading to localized and severe corrosion forms such as pitting and crevice corrosion. Detection requires integrated approaches combining visual, electrochemical, and microbiological techniques. Protection strategies include coatings, biocides, cathodic protection, and careful material selection. Understanding MIC and implementing proactive measures are essential for ensuring structural integrity, reducing economic losses, and maintaining operational safety. Research directions and innovations. Future work in MIC mitigation focuses on advanced detection technologies, environmentally friendly biocides, and smart coatings with antimicrobial properties. Research into microbial genomics and biofilm behavior will enable predictive models for MIC risk assessment. Development of real-time monitoring sensors integrated with IoT platforms can provide continuous data on microbial activity and corrosion rates. Additionally, exploring nanotechnology-based coatings and self-healing materials offers promising avenues for long-term protection. Collaborative efforts between microbiologists, materials scientists, and engineers will drive innovation in MIC prevention and management.